All right. This is a start for us that we are actually going to start moving towards much more of what calculus can get for us. Right? You're going to get used to seeing this particular graph. I use this one a lot to kind of describe to you how things are moving along, because what we do in calculus is instead of dealing with lines, we start dealing with curves. Okay, and we want to find rates of change on that curve. So if I pick 2 points, for example, maybe that one, which is a f of a, right? Because if I put a into the function, it gives me the y as a result, right? And then here's b f of b is that point. What I really want to find out is, one of the things I want to find out is average rate of change. So obviously I could find that rate of change right there, that rate of change right there, that one there, that one there. I could find all of them, correct? And then add them all up and divide by how many I found. But how many rates of change are between a and b? An infinite number. So is that really plausible to add them all up and divide by how many there were? Probably not. So what we do instead is actually quite simple. To find average rate of change, we just find the slope of that line. Because you agree, some of these are going to be a less slope. Some of them will be a greater slope. And some, at least once along the way, it'll be exactly the same if it's continuous, right? And basically it does actually average out just to be that line. Okay? And so for average rate of change, if you just pick a couple of points on there, it really is just that slope between those 2 points that I want to know about anyways. But I could find the average between there and there, but that's just not plausible. There's no way you would be able to do that. Could you maybe get close? Well, sure. But this is a way that'll give it to me exactly. That truly does find the average. Okay. Again, it really would then end up being change in y over change in x, correct? However much that was. You with me on that? And so what is this change in y value? What could I write this as in symbols? We could do f of b minus, nope, change in y. So not b, but f of b minus f of a, right? Isn't that the y values? Over change in x, which is down here. And what is the change in x value? You got to go in the same order. So b minus a, okay? Which may or may not be written down here. Nope, guess not. Average rate of change actually has another name, okay? And it describes this line here. We're going to see how much you remember from geometry. This line happens to hit the curve twice. Very good, secant. It's the secant to the curve because it hits it twice. Okay. So that's average rate of change over that. Maybe this is a time interval down here. Maybe A is 1 second and B is 3 seconds. To find the average rate of change over that period of time, I would just find that slope right there. Okay. Just find the slope between those 2 points of interest. Okay. Average rate of change, that's pretty important. So let's try a couple on that one. So let's determine the average rate of change for y equals x to the third minus x, because maybe this function here is describing how something is moving or how something is changing. All right? It's relating x and y for us on the interval -1 to 2. All right? Now, of course, we could get the graphing calculators out, right? But I'll just give you a nice little sketch here quick. If I put in -1, I get 0. If I put in 0, do you agree we would get 0? Right? 0, 0. Okay. And if we were to put in 2, I'm going to tell you it would be 6. All right? And I think it's, yep, if you put in 1, you also get 0. Very good. And so it kind of looks like this. Again, we could grab the graphing calculators, but unfortunately right now it's not on my computer, and so I can't really bring it up for you, so we'll just draw a sketch. Okay? That's how x and y are related based on that equation that we have. Y equals x to the third minus x. So what I really want to know is the average rate of change on the interval. Everybody clear that this is saying from -1 to 2 has x values, right? So it was -1 comma what? -1 comma 0 and 2 comma 6. So do you agree there are some positive slopes and rates of change in there, some negative, goes back to positive, and then gets really steep positive, right? So to find the average, again, we'd either have to add all of them up, which Well, let's face it, you can never do that. Okay? Or we just find the average rate of change, which will be just, wow, actually make a good line when you do it. Find the slope of that line. Is that a slope that I can find? Yeah, look at it this way. If it was negative 1 comma 0 and 2 comma 6, this is A, right? This is B in that formula. This 0 here is what then? F of A, right? I had to put A in to get it, and this is F of B, right? Changing Y over changing X, the same slope we've been doing for how long, right? So if we were to follow it, we would do 6 minus 0 over 2 minus a negative 1. And so what do we got? 6 over, add the opposite, 3. So the average rate of change on this function over that interval is 2. Or the average rate of change is 2. So even with those negatives, but you see how those negatives help to cancel out some of these steep positives, right? So come out to an average of 2. It might hit it more than twice, but it would be close. Yeah, the question was, wouldn't it hit it more than twice? It would be close. But I think my sketch is really bad. So, yep. Questions? That's average rate. That's how it changes over that interval on average, over the whole interval. Okay? Often considered more important, instantaneous rate of change. I kind of look at this as if you were on a roller coaster and for some reason at some instant the car just let loose. Which way would you go? That's what instantaneous rate of change is. Okay, if it just let loose, where would you go? Okay, so lots of physics involved there, right? Well, probably to the hospital, yes. Okay, but instantaneous rate of change is hugely important. But you notice I've changed the labels a little bit, correct? I have A and F of A right here. So really, this is the point I'm most concerned about. Is I want to know at that instant, how is it changing? Okay, and I want to know how is X changing as Y is changing, or how is Y changing as X is changing. So what you do is you kind of pick some arbitrary point out there. Notice I've said plus some X amount, right? So if you want to, for instance, let's say I said this point A was 1. This is kind of where point B was before, right? So what if I said this was 0.3? Well, what is delta X then? What's the change in X? Really, it's just 2, right? Because if I already had 1 plus 2, right? You see that? So this is also F of like that 3 for an instance, right? Just to give you some idea of how this works, right? So I look at it this way. To find instantaneous rate of change, I start pretty much the same way I did before. I start with 2 points. Yes? The question is, what's the importance of the delta symbol? And you'll find out. Yes. Really, the importance of the delta is I'm making it just random, any amount of change in X. Okay, that means I just have to pick some point not where I was before. Okay, so not A, F of A. Some other point is what that means. Okay, but it has more significance as we go further. Okay, because let's face it, we've seen delta X somewhere before in our slope formula, right? So that's more than likely going to happen. So here's how I look at it. If I were to find the slope between those 2 points right now, is that going to be a very good estimate for the rate of change of just that point? No. So I look at it this way. It's almost as if we're fishing. All right? I want to know about this point. I just kind of cast out somewhere. Oh, that's where my lure landed. All right? So what we're going to do is if I took the slope right now, that would be what I thought the instantaneous rate of change was. But what I'm going to do is I'm going to start doing what with that point? I'm going to start reeling it in. So all of a sudden, maybe the point's here. Now that's the slope. Do you think that's getting closer to what the actual rate of change is right there? Yeah, then what are we going to do? Reeling that thing in some more. Is this line that I'm drawing continually getting closer to what the instantaneous rate of change is? And then what am I going to do? I'm going to reel it in some more, and I'm basically going to reel it in until I get all the way back. Okay? Is really what we're going to end up doing. Okay? And here is where things truly get important, because I'm going to keep reeling it in until I get that, correct? What would be a good possible description of how that line hits the graph? It hits it once. That's called a tangent line. Okay? So instantaneous rate of change. The slope of the tangent line to the curve at any particular point. how we calculate that is going to be get rather interesting. Oop, there it is. So how do you think we could bring that? Because obviously, let's face it, if I bring it all the way back, we have a problem, right? Because if I reel that thing all the way back, I get those as my 2 points, right? If I find the slope between those two things, I get nothing, right? Because f of a minus f of a, well, that's 0 over 0. Well, that's just worthless. So what process is going to help me find this answer? A process we've been working on for quite a while, especially at the beginning of chapter 2. I'm going to find out what is the limit of that slope. As that I reel that point in closer and closer and closer, where is the slope going? Because I can't reel it in all the way because I end up with these 2 points here, a f of a, f of a. I got nothing. So I'm going to continually reel that thing in until I get really close. So it is the limit, and I'll make that bigger. That's just really small. Whoops. Helps if you hit the right part, though. Uh-oh. So here is, this right here is representing where I cast it out to, correct? The y value where that thing landed, minus where I started. Agreed? Now, whoa, what's up with this bottom? Why is it just delta x? How does that work? How's it just delta x? That's not fair. That's like cheating. Yeah, because if I do, the change in y is f of a plus delta x minus f of a, right? And the other one is, this is the first x value minus that one, right? So a plus delta x minus a. Okay. But here's a huge problem. What value do I really want to try and substitute in right there? 0. Because what? I want the change in x to be nothing, right? I want to reel it back in. That's what that means. The change in x to be nothing. Reel that thing in. And if you were here right now, you would see me actually reeling a fishing lure. Okay? But those listening to the recording, you don't see that. Okay? But I'm trying to put 0 in there. Is that a problem? That's a huge problem. 0 in the denominator, so we're going to have to learn how to deal with that. Okay? This right here is huge. Do you understand where I got this from in this problem? It's like the fishing analogy. I actually came up with that one too, by the way. I think it's a pretty good one, isn't it? All right. So then we already talked that this is basically the slope to that curve at that point. That's what it's called. That slope of that tangent line. So if I want to find the average, I throw it out there and I say from here to here, here's the average, just find the slope. If I want to add an instant, you have to reel that thing back in and find out where is it just at this point. But again, if you reel it all the way back in, you get a slope of nothing. There's nothing there. Okay? So what we're basically doing is we just keep reeling this thing in until I get close. And do you agree the furthest it can go is that line? That's the furthest it can go, is that line. So that is the limit. That is the furthest I can go, is that line. Okay? Let's try one. Calculate the slope of the curve for that. So that's how x and y are related. X squared plus 3 is basically our y value at x equals 1 and x equals negative 2. So now you notice, I just asked at particular points because I want this to be at a particular instant. What is it doing? So let's give this thing a shot. But notice what function I chose. I chose something that we know how to do. What is that? That's a parent graph that has been moved up 3, right? Okay, so it's x squared, so that's a parabola that opens up, right? So look something like that. Agreed? All right, so let's just do this one first. So this is basically my A value, right? You with me on that? That's A? All right. So at x equals 1, so we're right about here. So my answer should probably be like a positive of some kind, right? Because I'm looking for the slope of that thing. That's what I really want to know. That's the instantaneous rate of change. Okay? So what I have to do is basically kind of cast out there somewhere, right? So I'm going to cast out, maybe I cast it this way, maybe I cast it the other way, who knows? But I am going to add some x to it, right? Some delta x. I'm going to make sure it's not the same point. That's huge, all right? So it's the limit as delta x goes to 0, meaning I have almost reeled that thing all the way in. Okay, the change in x is almost nothing. So here we go. It's f of, well, a is 1, right? Plus some amount. This is the y value of where my lure landed, correct? You with me on that? Minus f of 1, because that's where I started from. Okay. I'm trying to follow that formula. Is everybody clear on that? I'm just putting a in, right? Over, what's the formula say on the bottom? Change in x. So here we go. Limit as delta x. Oh, my arrows are terrible. Delta x goes to 0. Is f of 1 plus delta x, is that something I can solve for? Sure. Put 1 plus delta x in there, right? Isn't that what that means? You with me on that? Okay. So it's 1 plus delta x squared plus 3 minus, and I always put brackets around this, so you might want to get used to that, minus f of 1. Is f of 1 something I can do? Yeah, you put 1 into the function. What do you get? Put 1 right in there. Right here. Yes, I have a question. Well, the first question, where's the 3 come from? I put, for f of 1, that means put 1 into your function. And function's right here. And I put 1 in for x, and I got 4.
Oh, so you take 1 plus 2 x.
And I put it in for x. Yep.
And then minus 1.
Yes. Perfect. The reason I put brackets around it is as we get more general with this, there's going to be equations in that bracket, which we will have to distribute the negative to. So if you just get in the habit of putting that bracket in now, you'll just always keep doing it. Okay? Over, well, unfortunately, delta x. If you hang with me, I will show you shortcuts in solving these, but you got to hang with me. Okay? Because I know this seems very algebraic, and it is. So the limit. Is it okay if I FOIL this out for you? Okay, so, well, it'd be 1 times 1 is 1 plus, everybody's good with that? So it'll be what, 2 delta x plus delta x squared? Somebody, that's me taking 1 plus delta x times 1 plus delta x like on scrap paper, known as my head. And then plus 3 minus 4. Wow, that's the worst delta ever made. Okay. Now, why am I doing all this work? Boy, it'd be great if substitution worked, right? Remember all those limit problems where we just got to throw stuff in and it just gave me the answer? That'd be awesome, but I still can't put 0 in for delta x because it's still on the bottom. Ugh. Delta x is just not hanging in there for me. Well, let's see what happens. Yeah, that's my best arrow today. Oh, that's all right. What do we got here? 1 plus 3 minus 4? 0. Huh. All right. So 2 delta x plus delta x squared all over delta x. Do you see anything that might be very advantageous for us algebraically? Every term on the board has a delta x in it. Yeah, factor it out. I think that is a wonderful idea. Limit delta x. Now there, look at that. I get on this side of the board, I can actually make a delta over here. It goes to 0. Let's factor out the delta x out of the numerator, and we get 2 plus delta x all over delta x. I just factored out the delta x like I was told. What can I now do with those delta x's? Delta x over delta x is, boom, 1. Sound effects optional when you do it. Can I now do substitution and substitute in the value that is of most concern to me, which is delta x being 0? Can I substitute it in right now? Yes. So you substitute it in, so this 0 can now go right there, and my final answer is 2. Wow, that was a lot of work for 2. What does 2 represent in this problem? The slope of that tangent line. So it is the rate of change. If the roller coaster let me loose at that point, that is the direction I would go. So am I going to stay on the rails? Not so much. You're going to go off into no man's land. Yes, staying on the rails is preferred. But if I was on this thing and I was coming around and I came through a loop and it let me go right there, well, okay, hit the line when you do it. But I would go off at a slope of 2 at that particular point. All right? And eventually gravity would pull me back down. But yeah, but for an instant, at that instant, that's the direction I would go. Okay? Well, we could figure that out. The question was, where would we land? We could figure that out. Okay? That's where it would let loose. Okay? Yes? Okay, the question was, and this is a great question, thank you, is would we get the same answer if we put -2 in? Well, let's analyze this. At -2, we would be at that point, correct? Would the roller coaster let me go at the same trajectory? No, it would not. So will I get the same answer? No, I will not.
If you put -1 in, would it just be -2?
Okay, good question there. If you put -1 in, would you get -2 because of the symmetry involved? Yes. Okay. In all graphs, will that work? No. In this particular example, because it is symmetric, yeah, it would work out that way. Mm-hmm. So, whew. We just said that that one was A. If we were to do the problem, which we're going to do right now again, we're going to make -2A. Yeah. So, well, you can always take another sheet of paper if you're running out of room. Or are you good? Are you sure you're good? Okay. So let's recap what I did. Okay. We took the limit as delta x goes to 0 because what does that really represent in our fishing analogy? Reeling it back in. Right? Hold on, I'm giving an analogy. No questions right now. All right. So what is this in our analogy? That's the y value where the lure landed. Now, if I stopped there and didn't reel it back in and found that slope, that's average rate of change. We don't want that right now. So now I'm going to say, all right, I'm going to subtract where I started because that's change in y, correct? All right. But now this limit is really what's reeling it in for me. All right. Down here at the bottom, it really is a plus delta x minus a, but we just know that's going to happen every time. Right? Or I could put the 1 in if you really want me to, but they cancel. Right? Over delta x. What is the biggest problem right now? Number one, I don't want to reel it all the way back in because I don't get anything. The other problem is that I'd like that change in x to be 0, though. But I can't do that. You see the problem? That's what I want it to be, but I can't do it. So we say, well, let's call the limit as it keeps getting closer and closer. So this would be as that line keeps getting closer and closer and closer, it keeps getting towards that limit, that boundary. All right? And so we keep finding a bunch of those slopes. But we let the limit process do it for us. So we don't have to do all of them. Okay? And so then what I did is I actually substituted it into the function to find algebraically what that y value would be, which it ended up being that. We subtracted where I started because that's change in y. I still couldn't put 0 in, but eventually all this stuff canceled out. I was able to put 0 in. If you do the calculus properly, you will always have delta x cancel so that you can substitute in your value every time. If you get down there and it doesn't work, you messed up somewhere. Now for your question, because my fishing analogy is now done. You sure? Didn't want to ruin it for you. Okay. I might have. Okay. So do you want to see -2 or not?
No.
No? Because I can tell you right now that the answer is -4. That's how fast that you're going to be able to do this once I teach you the shortcuts. Yes. Question. Yes. Once you have work like this, I would like you to find them both. Because I think it's very helpful to actually go through this work, because do we have a pretty good visual of what that answer should be for -2? And if I ended up with like positive 17 for that answer, we know something's wrong, because it's obviously a negative slope. Okay? Now this one happens to be that you just double it, but that doesn't always work, and I will teach you the shortcuts. It seriously will take you seconds to do these problems once I teach them to you, but you need to show me you can do it by hand. Yes? So that you can appreciate it. The question is, why do we do it by hand so that you can appreciate it and know where it's coming from so you're not just typing things into a calculator? The next question was, can we only have like 2 problems today? I don't know. We'll have to see.